In the previous video, we've seen some simple examples of computing work done for a constant force on particles moving in a straight line. And in those situations, we've seen that the change in kinetic energy is given by the work done by the force. It turns out that this is a general relationship which we are going to attempt to derive in this video. So there's going to be some complicated mathematics here, but at the end of the day, all we are doing is we are integrating Newton's second law with respect to position. So let's look at the situation here. In the most general case, you have a particle going from some point A to some point B. At each point on this path, let's say consider a general point here, there would be a force acting on the particle, and this force on the particle may be different at each point on this path. So to calculate work done, you need to evaluate this integral as we discussed in the previous video. You need to integrate the line integral along this line. You need to evaluate the line integral a to b of f dot dr. One important point here is that we are going to consider the work done due to the net force on this particle. So at each point, this force vector that I drew up is the net force acting on the particle when it is at that point. Okay, and according to Newton's second law, we know that the net force on some particle gives you the mass times the rate of change of velocity. Let's plug that into this integral and carry out this integration in general and see what happens. So here's what we have to do. If you have a particle of mass m and the net force on that particle is this F, then you can replace this F by m dv by dt, pull m out of the integral because the mass of a particle is a constant. Now let's do basically a change of variables. Because you know that the velocity of a particle is defined v equal to dr by dt, then you can write dr equal to v dt. If you plug that into this equation here, you can have the integration of from a to b dv by dt dot v dt. Now this you can write up as half of the differentiation of v dot v. Let's see how that works out, because you have d dt of v dot v can be broken up using something called the Leibniz rule. So you can write it like this. You can write d by dt of v dot v plus v dot d by dt of v. This is sometimes called the UV rule or the Leibniz rule, however you call it. But then, because the dot product is commutative for these real vectors, in other words a dot b equal to b dot a, you simply have 2 d by dt of v dot v. So in other words, dv by dt dot v is, carry this half to the other side, you have half d by dt of v dot v. So that was going from this step to this one. And then of course v dot v is just v square, or the magnitude square of this velocity vector, also known as the speed square, right? Now what step do we make in going from here to here. This is just the fundamental theorem of calculus. As you know from fundamental theorem of calculus, if you have d by dx of fx dx going from a to b is just fx evaluated at b and a. So you have fb minus fa. This is called the fundamental theorem of calculus, or I guess one of the fundamental theorems of calculus. In other words, from this expression you just get vb whole square minus va whole square. So you get half mv b square minus half mva square. But notice what we've found here. You found that the work done is the final kinetic energy, if the final velocity is vb, minus the initial kinetic energy. In other words, the work done by the net force is the change in kinetic energy. And this statement that we've worked out here is known as the work-kinetic energy theorem. So the work-kinetic energy theorem says that the work done on a massive particle by the net force, well, in brackets it's field because there's a force vector at each point. Well, the work done by this net force on this particle when the particle goes from point A to point B along some path. So when you do work, when you calculate work done, you have to consider the path, right? This work done is equal to the change in kinetic energy, that is the final kinetic energy at B minus the initial kinetic energy at A. In other words, starting from Newton's second law, we have proved that WAB equal to the change in kinetic energy. So notice that first of all, work done can be a positive quantity or a negative quantity. How do we make sense of that? Well, kinetic energy itself is always a positive quantity, but the change in kinetic energy can be positive or negative. In other words, kinetic energy can increase or it can decrease. So work done by the force field can be positive or it can be negative. Also notice that the work done may depend on the path you take. There are interesting cases where work done does not depend on path. We shall look at those in the next lecture. But in general, if you go from point A to point B along some path, then the work done by the net force acting on the particle is equal to the change in kinetic energy.